Okay.
Yeah, I was here till like 6 yesterday for some stuff, so I just figured
Yeah, it's always better to be in person, you know? Oops, sorry. How are you liking the class so far?
fine, I think. I've been out of school for 5 years, so I'm fine with setting stuff up. I get nervous about just like actually solving vector calc.
Oh, really?
So, well, I just use MATLAB for everything work, right? So I haven't solved stuff down like the examples we're doing in class. I imagine it'll get harder. So
Yeah. When we get to homework, let me know if you have any trouble, and I can work with you on some of that to catch up.
I think it's like I said, the examples and stuff have been like fine, like trying to look at the concepts. We'll see. I'm trying to study that shit. So.
Yeah, when you get to the homework is when you'll notice if things are tough. So let me know, and I'll sit and work with you on. I'll walk you through some similar problems, and we'll get you caught up.
Are you posting the first one today?
The homework, yeah, it'll be there right after class. How's it going? Good, good. Shelvan. Yeah. Not that problem today. You're coming by there, right? Yeah. What's it? The problem that we're on the TV going? Yeah. I've been trying to work on that. It's gonna be pretty exciting. I think it's a good way to go because we'll be able to. Yeah. We'll talk about it later. I'm excited about it though. Yeah.
Was midterm indefinitely?
Yes. Why is there?
No.
Okay.
I just.
It's for sure that way. Yeah, everything in that schedule will be upheld. Yeah. Huh?
Where it said, average over one period is somehow to be the real part, just the entire standard inside.
Yeah, so let's go back. You're talking about here, right?
Yeah, it's a 400. How do we know the drops that these two J omega close were at over one period?
So if you average over one, this is an oscillating function, right? Cosine and sine. Yeah, and this is actually a cosine function after you multiply by this, right? If you integrate cosine over one period, even if it has a bunch of frequency, what do you get? It's zero, right? Because you're integrating over one whole period, and it's as much positive as negative. Okay, guys, it is 9:30. Let's go ahead and get started. So recap what we did last lecture. What did we do? We derived the conservation of energy formula, and then it related an expression where we did a counting of possible power supplied by sources in a medium, right? So here's a medium of volume V, bounded by surface S with an outward normal N. We have electric and magnetic fields E and H. The medium inside volume V is described by constitutive parameters epsilon, mu, and sigma. We learned what those were last lecture. And inside this medium are two impressed sources, J and M. And this formula we derived directly from Maxwell's equations. Okay, the formula we derived directly from Maxwell's equations was the following. The divergence of the Poynting vector S, so the power leaving the medium, is equal to the decrease in power supply. So remember, by the concept of divergence, if we have a net flux exiting some volume, then there must be some, by conservation laws, there must be some quantity decaying in that volume, right? Because power is leaving the volume. So there must be a decrease in power density supplied by the sources, or there could be power dissipated in the medium, or there could be a decrease in the stored electric and magnetic energy densities. So that was the main thing we learned last time. We looked at a couple of special examples, and then We went into coordinate transformations and Eulerian angle transformation. We ended here. All right, so you're gonna have a paper to read as part of your homework on the Eulerian angle transformations. These are super useful and they've served me well in my career. So I think it's useful for you to learn them as well. There will be times where you can apply them, especially in antennas and reflector geometries and anything where you have, you know, two components. I have some kind of feed that's radiating and a reflecting surface, scattering problems, which we're gonna get to later in this course. So it's a useful construct for you to learn. Now we're gonna get into something else that's very useful, and it's called generalized curvilinear coordinates. So I don't know how many of you like geometry, but geometry is one of my favorite things. And what's really cool about this generalized curvilinear coordinates is it's based on parameterized geometries, right? So what do we have here? We have a parameter space, which is called U, V, and W. And we have a map, which takes us from, let me make sure I have a pen here. We have a map. So we have parameter space here, U, V, and W. There's a position vector R, right? R has three components. It's a vector. It's in this space. So some vector R here has an X, Y, and a Z component. And that X, Y, and Z component is dependent on the parameters U, V, and W, right? So it's a three-dimensional parameterization. So this vector R is a mapping from UVW space over to these components. This is X hat, Y hat, Z hat, right? This is a different way to list vector components. You could put them in as brackets and have commas separating the three functions. So there's a function G1, which takes you from UVW to the X component of the physical space. There's another function G2, which takes you from UVW to the Y component, and G3 takes you to the Z component. So if I have some point, here in UVW space, so this is U naught, V naught, W naught, for example, then if I evaluate this function at U naught, V naught, W naught, all three of these functions, then it will map over to some particular point in this space, right? And you can do that for all such spaces. So that's how the parameterization of the surface works. And we're going to use this construction in order to define generalized vector calculus formulas. We had before the divergence, the curl, and the gradient. We showed those, what their mathematical forms look like in rectangular, spherical, and cylindrical coordinate systems, which are the most commonly used in electromagnetic theory. But there are cases that might arise where you can look like a smart engineer, where you construct a new coordinate system, which is more suitable to problem solving. Maybe it has elliptical conductors in it. And in that sense, how are you going to integrate in that geometry or in that coordinate system? How are you going to calculate the divergence, curl, and gradient? It's not readily available on the internet, right? Probably you could find it somewhere if you dig deep enough. And right now we're going to construct all of these formulas, all vector calculus, directly in any coordinate system that you want. Okay, so what do we have here? We have this sort of surface geometry over here. We have what's called a V surface, a U surface, and a W surface. We have some point P naught here, right? That point P naught is the intersection between three lines. One is the U line, one is the V line, one is the W line, all right? So holding two variables constant and varying the third. So holding V and W constant and sweeping U through this parameterization, through this map, right? So if I hold U or V and W constant and sweep U, so say I would have some point, oh my goodness. So if I hold U and W here constant and sweep U along this line, then U and V are not, or W and V are not changing, but U is. That maps over to some line over here. That line is called the U line, all right? And that's shown here. All right. You can do the same thing for the V line and the same thing for the W line, and you can define some point P as the intersection of these three lines, right? So it's the parameterization. It's a map of the parameterized space. If you hold only one variable constant and sweep the other two, then you get a surface, right? So you would get the U surface, the V surface, and the W surface, for example. All right? So an example of these transformations could be transformation to cylindrical coordinates from rectangular. And our strategy is going to be to map everything to rectangular. And we'll do it in a general sense so that we can come up with expressions to do calculus and integration and vector calculus in these generalized coordinate systems. So for example, if I wanted to describe this position vector, which maps us from UVW into X, Y, and Z, my parameters for cylindrical coordinates would be U is equal to rho, V is equal to phi, and W is equal to Z, right? So over here I have U, V, and W are rho, phi, and Z, and I want to map that to X, Y, and Z, right? So how do you do that? Well, obviously we know that G1 function, which is a function of U, V, and W, is going to be rho cosine of phi, because now U is rho, V is phi, and there's no Z dependence for the X coordinate. Y is rho sine of phi, Z is Z. So the only reason I include this is to see what this mapping looks like for a particular example you're familiar with, all right? But we'll derive it in general. Okay, great. Any questions? All right. So how do we define tangent vectors? We already learned how to define tangent vectors, right? We differentiate this parameterization, but we saw it for 1D parameterization. We had one variable, one parameter, and as we varied that parameter, we took the vector derivative of that position vector, and we were able to define a tangent vector. Here we're doing the same thing in three-dimensional space. So a parameterization for the U line is where we hold two variables constant, V and W. So this is all V naught, W naught, and we vary U, right? So by varying U only, we parameterize a line. We trace out a line, which is called the U line in three-dimensional space, in the X, Y, Z space. If we differentiate this by the vector derivative operation that we've learned already with respect to U, we lead to a tangent vector directed along the U line, right? At P naught. So this tangent vector along the U line is here, and it defines the tangent vector at the point P because we evaluate the derivative at P naught. And we get the tangent vector to that line, right? Okay, you'll see why these tangent vectors are important next, or shortly. We can do the same thing for the V and the W. So how do we differentiate the position vector? We know the position vector R is G1, G2, G3. We need to differentiate that with respect to U because that is the line that we're interested in calculating the tangent vector of. We're allowing U to vary, it's the variable, the other are constant. So partial G1, partial U, G2 with respect to U, G3 with respect to U. Then we evaluate it at the point P naught, right? It's the same formula as we did before, the vector derivative. So if you take 5106, we're gonna do a lot of differential geometry because we're gonna learn the computational electromagnetics algorithm of geometrical optics, geometrical theory of diffraction, and so forth, which is very useful as well. So we'll come back to all this stuff. It'll get really fun. So TV and TW, you can do the same thing by differentiating the W line and the V line, right? So now we have three vectors here that are tangent to the point P naught, and this defines our right-handed trihedral, or our orthogonal coordinate system here, right? We have U, V, and W. Okay, so tangent means that this vector has the same, at least first derivative, right? It's a tangent vector to the curve. It's the normal definition of a tangent, right? A vector tangent to a curve. If I have, it's a good question on how to rigorously define it. I'd say it at least has the same slope as the curve at that point, right? There's the secant, it's like the first derivative, right? So the curve? Okay. All right, good.
What's the curve? Line?
Very good. Yeah, so the curve here is the U line, right? So if you haven't had much experience in parameterizations, then it might be hard to see. Let's go back to when we did the, let me see, how do I, like that? Yeah. Remember when we did the vector derivative, because that will help. Here somewhere, right here. Okay, so here, what did we have here? We had, oh man, sorry, 1 second. Geez, okay, so, I don't know why this thing's not, all right, anyhow, we have a path here, right? So this path is described by some position vector R. Now this position vector R is only a function of T. remember when we did the helix, right? Let's go back to the helix, which is I think here. The helix, the parameterization for the helix is here. R of t equal to cosine t of x hat, sine t y hat plus t over 3 pi z hat. So what that means is I have one parameter t, and I vary t in some parametric space. It'd probably be good to draw all that out since it's related. I don't know why it's not letting me erase things. Let me see if I go like this. All right, well, there's a parameter space here, which is the number line t. We go from A to B, right? This maps by position vector r of t over to some curve in x, y, z, right? So as I vary t from A to B in this parameter space, this vector here, r of t, maps me over to some curve in three-dimensional space, right? And one example of that is this helix. As I vary t from 0 to 6 pi, I plug it into these three functions. This is like G1, this is G2, and this is G3, and I get some vector. The tip of that vector is the position vector. The tip of that vector traces out the curve. So in this case, when we have the UV and W lines, so for here, for example, when we have these curves, we have now three parameters because we want to draw a three-dimensional object, right? We have three parameters, UV and W. We can vary each of these independently. And through these functions, G1, G2, G3, which are compactly notated as R, the position vector, we can draw surfaces or three-dimensional volumes in the physical space. By varying only one parameter and keeping the other two constants, I can trace out a line or a curve, right? And by the same thing as the vector derivative, if I differentiate the parameter describing that curve, then I get a tangent vector to that curve, right? Okay, great. Okay, so you get these three tangent vectors by differentiating the position vector. But now that we have three parameters, we can get three tangent vectors, right? Hopefully they're orthogonal, right? We're gonna restrict ourselves to the case when they are. So what we wanna do is to determine whether this coordinate transformation is admissible. And we'll define what admissible means. It means that there's a one-to-one mapping between the parameter space and the physical space. So if any one of the three tangent vectors are a zero vector, and they're also linearly independent, then the coordinate system is inadmissible, right? And we'll define that. That's what our definition is. So take that as an ansatz. If any of the three tangent vectors become zero, and they're also all three linearly independent, then we consider the coordinate system inadmissible. So a test which encapsulates these three conditions is called the Jacobian test. So you guys will have homework problem on this, and there will be a reading about it too that I've uploaded. So we have a Jacobian matrix here, which is all the derivatives, but put in a matrix form, and you take the determinant of that matrix and set it equal to 0. So we know that if a Jacobian matrix derivative, if the determinant of a matrix is equal to 0, then the matrix is non-invertible and thus contains linearly dependent rows. So one way to have three uniquely defined tangent vectors that we need for a right-handed coordinate system in three-dimensional space, we need at least three of these vectors to be linearly independent, right? We can't have just two vectors at some point and three at another point, because then the mapping of the parameter space to the actual physical space doesn't represent a geometry that has unique description at each point. So we need all three of these vectors to be linearly independent. And that's the basis behind this test. Here's an example, cylindrical coordinate transformation. So remember, UV and W is rho, phi, and Z. We have G1, G2, G3, rho cosine phi, rho sine phi, and Z, right? So let's try the Jacobian test for admissibility. We calculate all of these derivatives. Partial G1 with respect to U is rho. The derivative of this with respect to rho is cosine of phi. Partial G2 with respect to U is rho, so the partial derivative of G2 with respect to rho is sine phi. And then partial G3 with respect to U, this is not a function of U, so it becomes 0. It's a constant. And so forth. We can fill the entire matrix J, or we can fill this entire matrix, the Jacobian, then take its determinant And what do we find? We find that it's equal to rho, right? But the test for admissibility is that it cannot be equal to 0. So where then do we have a problem in the cylindrical coordinate system? When this is equal to 0, when rho is equal to 0, we have a problem. The cylindrical coordinate system is inadmissible. There's not a one-to-one mapping here, right? We know that. Along the z-axis, we have rho equal to 0. Along the z-axis, rho is kind of uniquely defined. It's equal to 0, right? Z is uniquely defined. We're going along the z-axis. But what is phi? Phi is multi-mapped, right? There's not a one-to-one mapping. There's all phi's are valid at that point, right? But phi loses its meaning. So that's one test. Great. Okay. Let's restrict ourselves to orthogonal coordinate systems. We want at each point to have uniquely like x hat, y hat, z hat. We know in cylindrical coordinates, we have rho, phi, and z. In spherical, we have r, theta, and phi, and they're always orthogonal, right? So let's restrict ourselves to orthogonal coordinate systems to make our life easier. How do we test for orthogonality of vectors, right? We take the dot product of any two given vectors, and we check whether or not that comes out to 0, right? So one other way to say this is if we calculate the angle between two vectors, we take the dot product and we divide by their lengths, because the definition of the dot product is, remember, the definition of the dot product is cosine of, TU dotted with TV is equal to cosine of the angle between them times the magnitude of TU times the magnitude of TV, right? So you can divide both sides by TU TV, and you get this formula here. So without the vector on top of this variable, it means the length of that vector. Okay, so for this to occur at right angles, we require that this is cosine of 90, which is 0. We can multiply this out to 0. We get TU dotted with TV is equal to 0. So TU dotted with TV, tangent vector of U was partial G1, partial U, partial GT, partial U, partial G3, partial U. That was TU, right? Differentiating tangent vector with respect to U. TV is the same thing with respect to V. When you take the dot product, you multiply the components and you add them. That has to equal to 0. We can do the same thing to test for VW orthogonality and UW orthogonality and WV orthogonality. All right. So these three conditions must hold for the coordinate system to be orthogonal. At all points in the space, these coordinates are, these three vectors, these three tangent vectors to all of the family of surfaces are orthogonal. So you might, okay, let me go back here. What are we talking about, this U surface, V surface, W surface? We're trying to talk about it in a super general sense, right? There's this U surface, V surface, and a W surface. But to bring it more tangible to something you're familiar with, these are families of surfaces that have the same value of some parameter on them. For example, here, what are these UVW surfaces in rectangular coordinates? They're planes, right? X, Y, and Z. And I have a family of planes. For every X coordinate, X equal to 0, I have a family, or the first plane. X equal to 1, I have the next plane. X equal to 3. So these are all different surfaces of, these are U surfaces, right? They're YZ planes that are at different X values, yeah? So what that would look like is a U surface here, we hold one variable constant, which is X, right? I hold X constant, I vary the other two, Y and Z. I get a U surface. I vary X to a new value, hold it constant, I vary Y and Z, or V and W, and I get another surface, right? Here's a surface, family of surfaces, UV and W surfaces for cylindrical. They are cylinders. At every different row, I get another cylinder, and I vary two of the parameters, and I keep one constant. Row, I keep constant, I vary phi and Z. I get a new cylinder, a family of cylinders. The other surface, half planes for phi, and I get full planes for Z, a family of stacked vertical XY surfaces, right? For the spherical coordinate system, we know we have a cone, family of cones. For the theta variable, we have a family of half planes. For the phi variable, and for the r variable, we have a family of spheres. And these all intersect somewhere, right? This right here, we have some spherical surface. This r equals to constant, which is U constant, and V and W vary, which is our generalized U surface. The sphere at some r equal to constant is some sphere. And then I have a line where I can follow, here. This is the U line, right? then I have a cone, and then I have a half plane. These three things intersect at some point, right? Well, here I have the same thing. U line, V line, W line intersect at some point. And I have these surfaces that also intersect. At that point, we define new vectors, tangent vectors. One is r hat, one is theta hat, one is phi hat. Those three unit vectors are orthogonal everywhere in space for rectangular, cylindrical, and spherical coordinate systems, right? We want to do this in a general sense. Why? It seems kind of a waste of time to do it in general, right? But what we're going to do is construct vector calculus formulas for divergence, curl, and Laplacian and gradient in this generalized system. And they're going to be functions of these three parameters called scale factors, where all we need to do is derive these generalized formulas in the generalized coordinate systems and as a function of these three parameters. And then once we know those parameters for each and every coordinate system, all of our generalized formulas collapse into the ones that we can use, right? These all have different divergence, curl, and gradients, and you have to memorize them all, but that's a waste of time. We'll memorize one formula, and we'll be able to reduce it to any coordinate system as long as we know what are called these scale factors, which we're going to get to. So that's the motivation.
Work with non-Euclidean geometry as well.
Non-Euclidean geometry. I don't. Okay. Yeah.
Yeah, the hyperbolic space.
Yeah. I'd have to think about that. I don't want to tell you something without thinking about it. But I haven't thought about that, right? I think even these are sort of non-Euclidean, right? Spheres, some of it. Okay.
We have to use orthogonal basis vectors.
Great question. You don't have to, right? I think this is the same kind of framework that general theory of relativity is framed in, right? We'll see the metric coefficients, some of the terms that are in Einstein's equations follow the same kind of geometry. And in that sense, I don't know if you have to have orthogonal coordinates. For us, we're going to want orthogonality. It makes things easier, and you're going to see why right now. So why do we need orthogonal coordinate systems, right? This is why. We need the scale factors. So let me introduce what the scale factors are, and then we'll see how they're useful. Because instead of memorizing all these crazy formulas, we just need to know these three little numbers, and we can apply those to any of our generalized formulas. We can do integration, curl, divergence, gradient in any coordinate system. Okay, great. So what is a scale factor? So first off, all right, so we have a differential displacement in the space. Let me see if I have a better figure for that. Must have skipped one slide here. Okay, so we have this differential length, right? Dx squared plus dy squared plus dz squared. We know that formula from this formula here. We know this formula from ordinary calculus, right? If I have some curve or space, if I have any three-dimensional space and I start at this point and I want to move to some other point, it doesn't have to be along any line or anything. I just want to move to another point. What is the displacement? What is the length of that displacement? Well, if I can break that displacement into an x displacement, a y displacement, and a z displacement, then that displacement is the hypotenuse of these triangles, right? So this is nothing but Pythagoras theorem. All right. So what do we have here? We're going to specialize this DL notation in rectangular coordinates to generalized coordinates. So x, we know, is G1 of u, v, and w here. So x is G1 of u, v, and w. Oh my goodness. X is G1 of u, v, and w. Dx then is by the total derivative, right? How can x vary? G1 has three variables, so we have to differentiate all three to find rise over run. Slope, rise over run, multiplied by a run in the u direction. That's not the only way that x can change. X can also change due to a displacement in v. X can also change due to a displacement in w, right? Okay, so this is the total derivative. So that's now dx in terms of G1 and u, v, and w, all right? Now let's square it because we need that square for our formula here. So let's square it then. And all we got to do is take the dot product of dx with itself, right? So to square this thing out, we have three terms. You can use this formula over here. A plus b plus c squared is equal to a squared plus b squared plus c squared plus 2ab, 2bc plus 2ca, yeah? So I've repeated all that here. This is the formula. Now, we could do the same thing for our dy and our dz. and we put them all together in this formula here, right? So here's dx squared, right? I put it up here. Then I calculate dy and dz similarly, and I take the square root of everything. So here over here is the square root, and you'll recognize part of g1 is here with respect to du. Here's the first term that goes here, and then here's the second term that goes here, that multiplies by dv. Third term by dw is here, and then there's the remaining terms. All right? Now comes the question of why is orthogonality useful? Because if you go back to the formulas for orthogonality, what do we notice? Partial g1 with respect to partial u, or with respect to u, partial g1 with respect to v, plus partial g2 with respect to u, plus partial g2 with respect to v, and so forth. Remember this formula here is equal to 0 when it's orthogonal. Let's go back to our DL, and what we see is we have that same formula here, right? So what we can do is say in orthogonal coordinate systems, this term is 0, and this term, and this term. So our differential displacement doesn't depend on, like mixed derivatives, if you will, right? I guess they're not mixed derivatives, but displacement in one coordinate does not equal to a displacement in another variable, right? So we end up with the top line only, and what we can say then is the differential displacement in generalized coordinates can be calculated with this formula, where we're now varying u, v, and w. Remember, in the parametric or parameter space, u, v, and w, I vary those three, and I get some displacement in the physical space. Well, h1, so we can write this dl here. This dl, the first line, because the second line is 0. We can write that in this form, where we've identified h1 as this component, h2 as that, and h3 as this. All right? Yeah, that's very good. This is like the it's the length. If I vary, so it's like the length of the tangent vector, right? You have so this is the tangent vector. Say I have the tangent vector. How do we calculate the tangent vector, right? Tangent vector, we differentiated g1, g2, g3 with respect to u. This is tu, right? And then if I square each of its components and take the square root, then it's similar to the length of the tangent vector in that direction.
It's the smallest we can measure.
Well,
Function more.
Yeah, so if I have a parameter space, oh my gosh, parameter space. If I differentially displace u in the parameter space and I go through the map R to the physical space, how long is that vector, or how long is that line, dl, in that direction from a displacement in u, right? Yeah, or path. So it's like a Jacobian, or it's like the determinant of the transformation, right? It's a scale factor. If I vary u in some parameter space, does dl vary in the physical space, x, y, z? These scale factors tell you how that happens, right? So these are super important, right? H1, H2, H3. This is all I need to know. And now we're going to derive generalized formulas for all of the calculus operations that we'll need. And all I need to know at the end is to calculate H1, H2, H3 for a specific coordinate system that I want to specialize these equations to. All right? Okay, good. So I know we're doing a lot of mathematics at the beginning, but it's super useful to get all of your classical theory, mathematical tools in place before we move on to the hard correlation magnetic theory, which we're getting to next lecture and so forth. So let's now look at vector calculus and generalized coordinates. All right, here are the formulas. You'll look at some derivations of these in your homework, but this is all you have to know now, right? And then you can calculate all of these operations in any coordinate system, and the ones that you're used to using, rectangular, cylindrical, and spherical. You don't have to memorize those formulas anymore. So you need to know what the scale factors are, H1, H2, and H3. And of course, you need to know the R mapping, the G1, G2, G3. But once you know those, you differentiate them, you get H1, H2, H3, and then you can evaluate any of these operations, right? So gradient is here, and you'll recognize this, right? Remember, you can guess right away, cylindrical coordinates. What is the gradient in cylindrical coordinates, right? Partial rho, partial
partial f partial rho, a scalar function. Let's call it psi. Partial rho plus 1 over rho partial psi partial phi plus partial psi partial z, right? So you can guess what the scale factors are. 1, rho, and 1, right? All right, good. So the divergence is given by this formula. The Laplacian is given by this formula. You can combine the previous two results to derive it. And the curl, this is super cool because every time I use the curl operation, I always use this determinant expansion, but I can only do it in rectangular coordinates, right? If you go to spherical or cylindrical, then I always go to the back of the book and look it up. But you could use this instead. Now you can use your same determinant expansion, but you need to know H1, H2, and H3. That's all. So instead of memorizing that, it's like a gnarly formula for spherical coordinates, right? Instead of memorizing that, I know how to take the determinant of this simple matrix. I just need to know H1, H2, and H3. And those are listed for a lot of coordinate systems. So you can calculate them very easily. Good. So here are scale factors for the common coordinate systems. Cartesian, the scale factors are all equal to 1. So U is X, V is Y, W is Z. These are all equal to 1. You can calculate all of these operations very easily, right? Here is cylindrical coordinates. U is R, V is theta, W is Z. And you have 1, okay, so there's rho or R, depending on what book defines it in what way, and 1, right? Exactly like we said. And you get all these formulas out of it. Here, we have R, theta, and phi, and we have scale factors of 1, R, and R sine theta. And you can get all of your vector calculus formulas out of the generalized formulations. Any questions? You're going to read a paper on this and do that in your homework. Why is this useful? What can we do with it? So let's look at this coordinate system here. This is called elliptic cylindrical coordinates, right? There are elliptical waveguides that might utilize this coordinate system. Or if you study raindrops and scattering from raindrops, raindrops are typically described by what are called prolate ellipsoids. So this one doesn't have variance in the sort of the in and out direction, but if this were a ellipsoid and still you have these hyperbolic planes in this z plane, then you could use something similar to this called prolate spheroidal coordinates or oblate spheroidal coordinates. There's many different coordinate systems that might be useful for, for the problem that you're solving. So how would you express the curl of a vector field in this coordinate system? If you were asked that before, you'd probably have no idea what to do, right? It's probably pretty difficult. How about the Laplacian? And furthermore, how would you solve the wave equation? We're going to see that in lecture 3, where we solve the wave equation by separation of variables. We're going to do it in generalized coordinates. And then you could separate the wave equation in any of the coordinate systems that allow it using this generalized approach, right? Which is super useful. We've basically solved all of the components that we need for electromagnetic theory in generalized coordinates, allowing us to do it in any coordinate system. We'll solve that later in the course. So here, all we need is the scale factors, right? That enables it to derive everything else. The scale factors here are, we have 3 coordinate variables first. We have an x, y, and a z axis. Here we have a variable psi, which is the angle, so to some observation point with respect to this xy plane, or xz plane rather. And then we have a variable eta here. This eta equals to 0. Oh yeah, so this plane phi rotates, right? This plane phi here, this vertical plane here rotates. It's the angle phi. Z equals to a constant is a plane that cuts this thing, right? So it's at this point I have this plane here, this big plane that's z equal to a constant. Then there's another z equal to a constant, and then there's some variable that must parameterize this here, eta. Eta is the variable that parameterizes the ellipse. All right, so the 3 variables are eta, psi, and z. Eta goes from 0 to infinity, and psi goes from 0 to 2 pi, and z goes from minus infinity to plus infinity, right? Okay, so the mapping is, what are these functions? X, y, X, Y, and z, right? This is G1, G2, and G3. G1 is a mapping that takes you from UVW to X, right? So U is eta, V is psi, and W is Z, which is not in here. So this is G1, this is G2, this is G3. So by plugging in different parameter values of eta, psi, and Z, you get different points in X, Y, and Z, right? You trace out all these surfaces. Okay. So what are the scale factors? You have to differentiate G1 with respect to U, which is eta. So if we differentiate G1 with respect to U, we get H1, which is this formula here. If we differentiate G2 with respect to, we have, actually, no, we need to differentiate all three, right? It's the length of the tangent vector. Let's go back. Here, G1, right? G1 is, or H1 rather, is the derivative of G1 with respect to U squared, the derivative of G2 with respect to U squared, the derivative of G3 with respect to U squared, and then take the square root, right? So let's do that. If we differentiate G1 with respect to U, it's the derivative of cosine hyperbolic. If you differentiate G2 with respect to U, it's sine hyperbolic. And if you differentiate G3 with respect to U, you get nothing. And if you take the square root of all that, you get this formula here. All right, that's H1. H2 is equal to H1, and H3 is equal to 1. So how do we calculate the curl in this coordinate system? We use our generalized formula, right? We go back to this formula here, and we use it at the bottom. Now we know H1, H2, and H3. We could do everything, right? That's all we need. Okay, good. So this formula down here is the formula for the curl. Okay, great. Any questions? Yes.
Might you encounter this type of coordinate system, like, I guess in terms of electromagnetics, if you see this?
Yeah, so here, this is like a rectangle, or sorry, an elliptical waveguide. So we have rectangular waveguides, cylindrical waveguides, and then there are spherical cavities and things. There are also elliptical waveguides, and the functions, the special functions that we'll see, we're not going to solve that in this course, but I pointed out that the special functions that describe fields inside of these elliptical waveguides are called Mathieu functions, or Mathieu, and they do show up, right?
So not generic enough, right? You could use it for spherical waveguide too.
Yes.
Parameters.
Yeah. All you need to know is H1, H2, and H3 for rectangular, cylindrical, spherical, any coordinate system, and you could directly use those. Great. Okay. How do we integrate, right? So to integrate along a line over a surface and throughout a volume, we need differential arc lengths, different surface areas, and differential volumes, right? dV, ds, and dl. So we can easily accomplish this in any coordinate system using the generalized coordinates. dl, we already know what that is. We derived it, right? That's how we define these scale factors H1, H2, and H3 in orthogonal coordinate systems. ds now is equal to, so this is ds in the physical space, the XYZ space. It's equal to H1, H2, du, dv, right? For example, for a ds that is orthogonal to, which is if it was a ds vector, it would have a u vector, right? And then dv is just du, dv, dw with the Jacobian in front. This is a standard for coordinate transformations. You probably have seen this before. And that's equal to H1, H2, H3, du, dv, dw in orthogonal coordinate systems. Yes?
So there is a problem with DL like that. If you cannot solve that root square formula, how do you want to solve the integral? Because that doesn't have any closed form.
If it doesn't have a closed form expression, you will be able to calculate. Okay, so the whole integral doesn't have a closed form, right?
Yes.
Yeah, that you'll have to worry about when you get to a problem like that. Most likely, you should be able to integrate it, depending on what function you're integrating against, right? That is definitely a possibility. You might have to numerically integrate it or so forth. Not all integrals have closed form expressions, but if you needed to set up the integral, you could do that. Very good. Any other questions? All right. Hopefully we can get to, I'm going to skip over metric tensor. You don't need it yet. It's exactly, all it is it's the same thing as the scale factors, except it's the square of them. You can read this later. This is more for like relativity and things. So what it kind of shows you though is if I have a DL, this little red line here is a DL in UVW space, how long, what is the scale factor for that DL in XYZ space, right? How much does it stretch by? How much does the coordinate transformation stretch that differential displacement of the parameter space? And those are typically described by these things called metric tensors. You'll see this metric tensor, G. This is in general theory of relativity. Okay, great. All right, guys, let's move on to our next lecture. Whoops. One second, let me open up our next lecture here. All right, very cool. So we're going to get into, why is it taking so long? We're going to get into media. And let's see here, Dropbox. All right. All right. Let's see, play show here, slideshow. Okay. All right. So lecture 2, what are we going to do now? We're going to study the electrical properties of matter, right? So we have material media that we define with epsilon, mu, and sigma, but now we're going to study how, what does epsilon, mu, and sigma mean? How do we define those? How does electromagnetic waves interact with matter? So we're going to study the electrical properties of matter first. Here are some references that I used to create these slides. So let's start super basic. We have the atom and the elements, right? Periodic table of elements. This periodic table of elements will tell you what the model of an atom is and how many electrons exist around in different various energy levels or shells around the nucleus and so forth, right? You guys have seen this before, so I don't want to spend too much time on it, but periodic table, we're starting with atoms, right? We need to understand the atom first and how it's constructed in order to study its interaction with light and electromagnetic waves. So the Bohr atomic model of an atom, we have the nucleus, right? There's protons, neutrons. There are electrons orbiting this nucleus in predefined orbits or shells in the Bohr atomic model, and they are confined to those shells. If the atom absorbs any kind of energy or releases energy, the electrons can jump from one shell to another, releasing photons, right? So here, for example, is sort of the Bohr atomic model for a hydrogen atom, which has one electron and one proton in the first shell. Then we have this one here, which I think is silicon, I think. Is there 4? Nope, this is not silicon. This is silicon. 4 electrons in the outermost shell. We have 14 protons and neutrons in the nucleus. The first shell has 2 electrons. The next shell has 8. And in this particular atom, we have silicon, which has 4 sort of valence electrons that allow you to construct or construct covalent bonds, right? Okay, so the electrons of any atom exist in only discrete states, possess discrete amount of energy, and to the discrete radii of their corresponding orbital shells. We can move from one level to a lower one. We release a quanta of energy in the form of a photon, or if we go from a lower to a higher, we absorb a photon. And if an electron maintains its orbit, it neither absorbs or radiates any energy. Okay, let's define a few things that we're going to use in the study of electromagnetic theory. We have convection current density. So what is convection current density? That's the current density associated with clouds of electrons, right? Clouds of electrons moving through some screen. So they might not be bound to a conducting volume. So assume that we have some volume charge density, right? QV is distributed uniformly in an infinitesimal cylinder of cross-sectional area delta S and volume delta V. All right, so these charges, this volume charge density is distributed uniformly in this infinitesimal cylinder. The total electric charge within a volume V, we integrate the density, right? that is moving in the z direction with a uniform velocity vz. So some kind of charge density, could be a cloud. It's moving in the z direction with a uniform velocity vz, right? So we want to calculate this quantity here, which you can define, called the convection current density. But how is that defined, right? So first we have calculate this quantity, delta QE, which is the total charge, right? Change in charge with respect to change in time is equal to delta QE. QE, remember, is the total charge. The total charge is the density of charge multiplied by the volume. The density of charge is in coulombs per meter cubed. We multiply these two, we get the total charge density. Delta T stays the same. Delta V can be written as delta S, delta Z, where delta S is the cross-sectional area. Delta Z is some differential displacement along the Z-axis. And then we have, we can rearrange this so that it's QV delta S, and then we just have delta Z by delta T, right? Because delta Z by delta T is a velocity. So now we're gonna say the change in current is equal to the limit as the time step goes to 0 of delta QE over delta T. We just defined that to be QV delta S, delta Z over delta T, right? And we can say that this is QV comes out, delta S comes out, and we have the limit as delta T goes to 0 of delta Z over delta V, which is the velocity, right? The derivative of position with respect to time. So velocity. All right, so that's the change in current, right? Is QV, the change in S, or a differential displacement, a small amount of current is delta S, right? Times the velocity times the charge. So what does that tell us? That says that the amount of charge that's moving, the charge density that's moving at some velocity V that passes through a cross-sectional area, delta S, defines our DI, right? Defines our current. Our current is defined that way. Current is the amount of charge passing through a cross-sectional area with respect to time, right? Yes?
So the discrete, or so if we're doing differentials, and it's sort of a mathematical construct like an average flux, or are these discrete charges?
Okay, so when you define the charge density like this, normally you're defining it as a continuous charge density distribution. If you had discrete charges, you'd have to sum them up. But here I think we're considering sort of a distribution of charge is continuously defined.
Probability distribution.
And maybe not probability, right? It has a physical, it has a unique number. It has a deterministic number, right? Okay, so divide both sides by delta S. Why? Because here we have units of amperes. We want to define a density of current now. So we divide both sides by delta S, take the limit, and we get the current density now, which is defined as the charge density moving at some velocity V. And we can define that for the entire structure now, right? Does everybody understand what we're doing here, right? Okay, good. We're trying to define current in the sense of flowing of charges through a surface, a cross-sectional surface delta S. Similarly, for the X and Y components, this was JZ because we're considering the charge moving in the Z direction, this charge density. We can do that for all three components, construct a vector out of them V, and then we have J equal to QVV, yeah? So that is the definition of what we call convection current density.
And this ignores eddy currents that are orthogonal to. So we had an eddy current going around it.
Yeah, we're assuming that the X component of current density is developed from the X component of velocity, right? Okay, good. So now let's specialize in the case of conductors. All right, so what do we have here? Due to the nature of metallic bonding, the electrons in a conductor without an external applied field will be directed in random directions due to thermal motion. No current. That's what this picture is, right? It's called the electron C. Each of these atoms that comprise of a conductor give up one electron to the electron C, right? These electrons are free to move about the lattice. And when there's no applied external field, each of these electrons are moving around in a random direction. Since they're moving in random directions, they constitute no current, right? There's no current. When an external field is applied to the conductor, the the charges will move to the surface of the conductor to satisfy the boundary conditions, which we'll study, or we have studied. They move very quickly. To see this, consider placing a charge rho v naught inside of a conductor that is subjected to an external applied field. So I have some conductor, I impress a charge density at the center of that conductor, and I want to calculate the dynamics of what happens to that charge density. So what do? We have charge continuity equation. The divergence of J is negative partial rho partial T. We know this for the charge continuity equation. From here, we can substitute the constitutive relation J equal to sigma E. We have the divergence of sigma E now is equal to minus partial rho partial T. And then we can say that sigma is not a function of position. We can factor it out. It's missing that part here, right? No, here. So we can factor sigma out and divide both sides by it. Now we have divergence of E is equal to minus 1 over sigma, partial rho partial T. Now we apply Gauss's law. We know what divergence of E is equal to, right? Divergence of E is equal to rho over epsilon. So rho over epsilon now is minus 1 over sigma partial rho partial T is equal to 0. And then here we can say that partial rho partial T plus sigma over epsilon naught equals to 0 by applying this Gauss's law here. So that's what we've done here. No, what have we done here? I think there's some mistake from going from this line to that line.
Equal minus.
Yeah, this should be an equal, right?
Equal minus.
Okay. So divergence of E is equal to this. That's correct. Then we say that the divergence of E is rho over epsilon. That should equal to minus. There's an equal sign missing in here. So, okay. Let me add that. So there's an equal sign here. Missing. Okay, good. Now, what can we say? Rho, so what we're going to do now is we're going to multiply by sigma and divide by epsilon, right? No, multiply through by sigma. That's all we did. So if you multiply through by sigma, partial rho partial T plus sigma over epsilon rho is equal to 0. This is a differential equation that we can solve. What function, when you differentiate it and add it back to itself with the scale factor, gives you 0? The exponential function, right? The exponential function is equal to its own derivative. So what we get here is rho is equal to rho v naught, some constant, and then e to the minus sigma over epsilon naught T. So what does that mean? That means that if the conductivity is very high for a metal, right? Ideally infinity if you have perfect conductors, then in a very small time instant, what's going to happen is that charge is going to decay to 0, right? At every point within that conductor. So the time TR, relaxation time, that it takes for the free charge density placed inside a conductor to decay to e to the minus 1. 1 over e of its initial value is, or 36.8% of its initial value is known as the relaxation time constant. All right. So it's dependent on the conductivity. All right. So what does that mean? If this is a solid conductor here, sigma is ideally infinity right here, right? So if sigma is ideally infinity, if I place a charge density inside of that conductor, the charges are going to decay from each of those points and they're going to move, right? They're going to move under the influence of the applied static electric field to the surface of the conductor. So what we see here is that all of these red dots represent charges. The electrons are moving to the surface of the conductor. Positive charges are on the bottom side of the conductor due to an applied electric field. All right, good. So the surface charges induce an electric field internally, EI, such that the total field, E total, is equal to E applied plus this induced field is equal to 0. All right, great. And we can see that here, right? So, okay, let's think about this, right? I apply an electric field. Where's the electric field applied? This electric field here, EA, right? Here's EA, yeah? I apply it to a conductor. What's going to happen? We know that the charges are going to move to the surface of the conductor. So all of these electrons, they go in the direction of the negative of the applied field, right? The positive charges go in the direction of the electric field. So all the positive charges are going to show up at the bottom of the conductor. The negative charges at the top. We know for the boundary conditions that D, the normal D terminates on charge, right? N dotted with D2 minus D1 is equal to rho sub S. We derived that. So we know that D inside is equal to 0. So n dotted with D2 on a conductor gives you rho sub S. So here's a line of D, basically a line of E related to D, which terminates on these negative charges, and then they emanate from the positive charges, right? When the negative charges build up on the upper surface and the positive on the bottom surface, there will be electric flux generated. The electric flux goes from positive charge to negative charge, right? So inside we have opposing electric field than the applied. Applied is assumed to exist everywhere, right? When you add these two, you get 0 inside. 0 electric field inside the conductor.
You still have charge inside because you just have the charge separate to cancel the field, but it may not be like all of the charges added to separate, cancel that. If just some of it is separated and that already produced the opposite field.
That's a great question, and I like the way you're thinking. My answer to that is no, based on this expression here. If you have any conductivity, the charges are going to move. They're going to move away, right? They're going to move away.
The bottom face actually experience a influencing electric field when the EA exists.
Yeah, EA is everywhere, right? The charges that are forced to go to the surfaces conspire to generate an internal electric field or an induced electric field, such that the superposition of the applied electric field and the induced field give you 0 field inside.
So all of the metal experiences all of the electric.
Yes.
Atoms are shielding.
Yeah, exactly. You can also think of Gauss's law here. If I made a Gaussian surface that would surround inside the conductor just under the surface, then there would be no charge there, so the field would be 0, right? Because all the charge went to the surface. Okay, great. Questions?
So if there's no external electric field, could I have charges in the middle, even with perfect conductivity? Or
Yes. Yeah, if there's no applied electric field, then there are charges that are floating around inside, right? This is assuming that we have some charge impressed into the medium and under the influence of a field. Great. So we have a current density, right? Divergence of J. We started off with assuming that there's some flux throughout each point. So let's define what we mean by conductivity. When a conductor is subjected to an electric field, the electrons still move in random directions, but they drift slowly with the drift velocity V sub E in a negative direction of the applied field, right? Electrons go in the opposite direction of the applied field, thus creating what we call a conduction current. So now this is different than the convection current. We assumed we had sort of a gas or a charge density, charged gas that moves through space with some velocity V. Here, we're assuming we have conduction current where the electrons are flowing through a conductor. So the applied electric field E and drift velocity VE of the electrons are related to this formula. We apply a field E, right? We get the electrons to move with the drift velocity in the opposite direction of the applied E. That's what this negative sign is. But then what is the proportionality constant, right? Different conductors might give you different velocities for the same applied field. So there's some proportionality constant, which is a characteristic of that metal that allows you to construct or to relate these two, which is mu sub E, called the mobility, the electron mobility. All right, the electron mobility is always a positive quantity and has units of meter squared volt second, all right? So if we use this concept back in our convection current density formula, we could say that J is the electric current density is equal to the electron charge density multiplied by the velocity. And we can now say that the velocity is equal to minus mu E. So we can plug in minus mu E here. And we can define what we call the static conductivity of a metal. The static conductivity is the proportionality constant between the applied electric field and the resultant current density, right? This is a proportionality factor. Different materials or different metals have different static conductivity. So we're talking about static fields here first, where we apply a static field and we get the electrons to drift slowly through the metal. And different metals have different conductivities. We know that. And this is our constitutive relation, right? So we stated it in lecture 1, J equal to sigma E. But here we're defining it. What does sigma mean? How do we derive it, right? We start with this gas of electrons that flow in some direction with the velocity V. Then we specialize to the case of a conductive medium where these conductive electrons are moving in response to an applied static electric field. They drift in some direction. There's a proportionality constant which describes how fast they drift with respect to the strength of the applied field. We know the direction is anti-parallel, and we can then say with the same formula, J is equal to Q times V, right? Or this could be rho times V, charge density times the velocity, which is conduction current. Now we're specializing into the case of conductors, and we get this formula, which is J equal to sigma SE, static conductivity with an S. We'll study dynamic conductivity shortly.
This was not the concept of resistance still. So
No, this is, right? I mean, sigma is a conductivity. If you invert conductivity, you get resistance, right? So it has the notion of, it's an admittance, right? It has the notion of.
a superconductor, do we have infinite electron mobility? How does that make sense if we only have finite electrons?
Yeah, superconductor, okay. Let me think about that before I answer you on that, superconductor. But I know superconductors are characterized by having no resistivity. So I think there's more at play than just the classical models, though, for that. But yeah, come by my office, we can talk about that. Okay, very good. Yeah, it's a measurable quantity, right? You can measure this for different materials. And then if you can define sigma in terms of it, right? If you know the charge density of a particular material, which you can find from the nature of the atomic lattice or the makeup of the material, then and you multiply it by this mobility, then you can define what the conductivity is. Yes?
And that's not necessarily uniform through space.
Definitely not necessarily, right? This is a point relationship here. This is evaluated at some point, right? These densities and these mobilities. It could be an inhomogeneous material that would have an inhomogeneous conductivity. That's true. Any other questions? So we start with the easiest one, right? J equal to sigma E. We're gonna get a little bit more complicated here. What about dielectrics? All right, so we call these insulators. We studied conductors to allow electrons to flow freely through the lattice, but here we're going to talk about insulators, which is the converse, and we call those dielectrics. So what happens in a dielectric? We don't have any free charges that can flow around, that can drift in response to an applied electric field and acquire some velocity. Instead, what we have here is the concept of bound charge, right? So if I apply an electric field to some medium here, for example, that's comprised of atoms, right? An atom here without an applied electric field, an ideal atom has a nucleus and an electron flowing around it, right? And everything's symmetric. So we can assume that there's no net charge density. Each of these atoms have, since there's no net charge density and everything's symmetric, then there is no generated electric field, no induced electric field. We'll see what I mean in a second. Here, when I apply an external electric field to a dielectric material, what happens? Well, the electron that's orbiting the nucleus is now going to experience a force, the electric force, which causes the electron to move in the direction opposite of the applied field, right? It's still a negative charge. It's just not free to drift in the conductor. Now it's still orbiting the nucleus, but instead of symmetrically orbiting it with no applied field, it's going to take an elongated path because it's going to stretch that electron cloud. This is a classical model, right? It's going to stretch the electron cloud in the direction opposite of the applied electric field, right? What does that do for us, right? What that does is it separates the symmetry of the plus and minus charge. And as soon as you have separated plus and minus charges, then an electric field is going to be generated that starts from the positive charge and goes to the negative charge, right? That's what electric fields do. They remember the divergence of D is equal to rho. And the divergence operation picks out sources or sinks of vector field D, right? So the divergence of D, by applying that operator divergence to the electric flux density vector field D, it tells me where the sources or sinks are, and those sources or sinks are rho, which is charge. So every time I have a charge, it's a source of the vector field D, or a sink if it's negative, right? So if I have two charges now, I have a plus and a minus, then these become sources and sinks of vector field D, or I can say that an electric field is created. So the induced electric field, which we're going to study in a second, is in the form of what we call an electric dipole, all right? So when EA is applied, these charges do not move to the surface in a conductor. They're bound to the atom. But rather their respective centroids, they shift slightly in position relative to each other. It's an infinitesimal distance. So now we're going to define a dipole moment of how we can model this. So a number of static electric dipoles formed, right? And each can be represented as a dipole with moment dpi. What is a dipole? A dipole is when you have a plus charge and a minus charge, 1 plus, 1 minus charge, separated by some infinitesimal distance, right? That's a dipole. Like a magnetic dipole would be north and south poles separated by some distance. An electric dipole has a plus charge and a minus charge and some distance, right? So we have plus Q minus Q. We call this dipole dpi because it's a differential or small amount due to an electric field that's applied for each individual atom. As Q, the charge of the dipole multiplied by L, which is the separation distance between them. And these are vector dipoles, right? They have the vector quantity, an arrow. Now the dipole moment points from minus to plus charge. You have to be cognizant about that because normally the electric field goes from plus charge to minus charge, right? When I apply this electric field here, E applied, the minus charge goes in the opposite direction of the electric field. We're assuming that the positive nucleus is heavy and stays fixed, right? So now the generated or the induced electric field is going to go from plus charge to minus charge, right? The induced electric field goes from plus to minus charge. But the dipole moment, the way we're defining the dipole moment is from minus to plus because this L vector is defined in that direction.
What's the moment? If we have non-s orbitals like an energized ion, would the moment be the same? Because if it's carrying.
Okay, so some other orbital you're saying?
There's some other orbital that perhaps the electron is in some other place, so the momentum is different.
Okay, so whatever orbital that this electron is in, that orbital is going to get its symmetry shifted. We can define some displacement with respect to the center of charge, of the positive charge and negative charge in the classical model, right? Thinking of it in terms of orbitals is probably beyond this model, but you can do that, I'm sure, if you consider it.
You can have a ring, or I guess you could have the moment vector on orbiter.
Okay.
The atom is energized.
Yeah, we'll have to think about that. Okay, yeah. So I don't want to confuse people yet with the different cases, right? Let's consider this case where we have the classical atom and we just stretch the nucleus. When we get to orbitals and things, if you want to discuss that, we can, which will be a little bit beyond this classical model. Okay, so what do we have here? If we have a material with the applied electric field equal to 0, there's no induced dipoles inside. Everything's symmetric. The electron cloud is flowing around the nucleus in a symmetric way. If we apply an electric field, EA is not equal to 0 now, we induce a number of dipoles inside the dielectric, right? We're going to account for the field generated by all of these dipoles external to the medium in terms of what we call the permittivity. So what we're getting at is, what is permittivity? If someone asks you what is permittivity, you say dielectric constant is associated with some dielectric and allows me to account for, the electric flux density related to E. But here we're going to define it much more rigorously and physically. Okay, so we have induced electric dipoles inside of a dielectric medium, right? Okay, so the presence of these dipoles can be accounted for by developing a microscopic model in which each individual charge and dipole is considered, right? We could do that. Such a procedure is very impractical though. We wanted to calculate the field due to every one of these dipoles. You can do that, right? In the previous electromagnetics course, you studied how to calculate the electric field or the electric scalar potential of a dipole, right? You could add up all the dipoles in this entire medium. Once you apply an electric field, you have these static dipoles. They generate a potential at any given observation point. You could add them all up. That's an impractical process if applied to a dielectric slab because the spatial position of each atom and molecule of the material must be known, right? Instead, in practice, what we're going to do is model the behavior of these dipoles and bound charges in a qualitative way by introducing an electric polarization vector P, which is a macroscopic model involving thousands of atoms and molecules. All right, we're going to average basically, right? We're going to define this vector field P. It's a new vector field P as it's going to be associated with every point, right? P has a definition of every X, Y, and Z. So if I give you this X, Y, and Z, it has to be in a material we're going to see. You can define the vector P at that point. That's why we're taking the limit process as delta V goes to 0. So some volume we're going to consider in this medium. We're going to consider some volume. We're going to add up all of the dipoles in that volume, right? And then we're going to divide by the volume and take the limit, which basically says it's the number of dipole moments per unit volume, right? At any given point. This is going to be a vector field P. So it's continuous. It's defined everywhere. It's a new vector field from an average of a set of discrete dipoles. All right? We'll see why that's useful. Instead of adding up all the field due to all the dipoles, we're just going to define this new vector field P, which accounts for all of them.
So we're extrapolating and assuming it's homogeneous.
Doesn't have to be homogeneous, right? This can have a different value at different X, Y, and Z's because we're summing up dipoles within some volume delta V, but if we move to another point, there's a new delta V associated with that point. It could have a different number of dipoles. It could be an homogeneous. All right. What is this polarization field? Let's define it a little bit more rigorously. We have, the question then is, how do we find the polarization field P, right? How do we define the polarization field P? Assuming an average dipole moment of dpi, right? So this is the dipole moment. We're going to average it now. We're going to say that that's Q times some L average, right? Because dpi was Q into L sub I, right? The ith displacement. Now we're going to say, well, if we're going to average all the dipole moments, then we're going to consider an average displacement. So, and then same Q for all of them. We're just going to define one displacement, which is the average of all the displacements. Okay, the electric polarization vector can be written when all dipoles are aligned in the same direction now as P, defined by delta V go to 0, sum of all the dipole moments per unit volume. But now we know that this is some average value, it's constant. We can add it up and multiply by NE then, right? The number of dipoles in that volume. We get NE times dP average, because these are all the same. All right, then we can define by dP average, we can say NE is QL average. This is the number of dipoles per unit volume. This is the average displacement relative to the charged centroids.
You define Q.
Q, yeah, that's a great question. It depends on the medium, right? It depends on the particular material. We won't need to get that deep with it. What we're going to develop this classical model that defines what permittivity is, and ultimately permittivity is going to be a measured quantity, but it'll fit this model, right?
We have a distribution vector.
A distribution vector of polarization at each point.
Instead of averaging it to one number, we have polarization of angles. So
You mean like an anisotropic material? Polarization could depend on direction? Yeah, that's possible. That's anisotropy. Here we're considering isotropy. We'll get to anisotropy. We will. Then we're going to consider in terms of its permittivity being different in different directions. Very good. Good question. We still need to know the average distance, L average, though. Okay, so I think next lecture we'll come back like 2 slides and recap, and then we'll get into the derivations here where we define what this polarization field P is and how we can use it to define epsilon, the permittivity of a material. And then ultimately we can understand what D equal to epsilon naught E is, or epsilon E is. And from there, we can use that constitutive relation to calculate the interaction of fields and matter, right? Okay, good. There's a homework out. It'll be out on Canvas shortly. It's due in 1 week. There are reading materials. I'll tell you what you need to read in the homework assignment that are also on Canvas. Those are already there. And let me know if you guys have any questions by email. You can reach me for sure. All right? Or you can come to my office. Just come to my office and come in. All right, guys. Very good. Xiaofan, when did you want to You want to come on my office at, what time is it? 11? You still want to come at, yeah, just come at the normal time, I guess. Okay, all right.